Welcome. And so you were just looking at and learning about electronegativity as a periodic trend and how electronegativity and specifically the differences in electronegativity can be used to predict the type of bond that can occur between two atoms. And so if we think about those electronegativity difference going on kind of a scale, the larger the difference, the more likely you are to form an ionic bond. Covalent bonds, where you're sharing electrons, the sharing of those electrons can occur in really two different forms. You can have what's called a nonpolar covalent bond, where you have a very small difference in electronegativities. So you have two atoms that have almost the same electronegativity value. And they're so evenly matched that they both have the same attraction and affinity for electrons in a bond. And so they share those electrons evenly. And we can see that in this picture where the blue is actually representing the density of electrons. So the more even the coloring of that blue region, the more evenly those electrons are shared. And so that's different than in a polar covalent bond, where the electronegativity differences are a little bit larger, and they're large enough that one atom has such a higher electronegativity and such a greater attraction for electrons that although it still shares, it's stingy and more of the electrons are around that more electronegative element or atom more often. And so we see that. Notice the shading is not even. There's a lot more blue shading around the atom on the right than on the atom on the left. The atom on the right would be the one with the more electronegativity with the greater attraction. It doesn't have it's still sharing those electrons. It's just that it has such a stronger attraction that it uses them more often. It takes them more often. And we see that we have this uneven distribution. The electrons don't move around both atoms in the same way. They're kind of over here around the more electronegative atom more often. When we have that situation, we have what's called a polar covalent bond. And we label that bond. Sometimes you'll see this arrow, and the arrow always points towards the element with the higher electronegativity, and the plus sign is always on the side of that the bond with the atom with the lower electronegativity. You'll also see these Greek letters. This is a lowercase delta, and this is read delta plus and delta minus. These are used to label the elements in the bond. The higher electronegativity element gets labeled with the delta negative. The lower electronegativity element gets labeled with the delta plus. This means that they have a partial charge. So they're not ions, but because the electrons aren't shared evenly, the side of the bond with the higher, more electronegative element will behave as though it has a little bit of a negative charge because there are these extra electrons hanging around it more often. And the opposite side gets left a bit deficient because those electrons don't want to be around that atom as much. And so it has a slight partial positive charge to it. And in a minute, we'll look at some simulations to see kind of what that means, right? When you have a really large difference in electronegativities, that's when you get an ionic bond, right? That's when the difference is so much that the element with the higher electronegativity has such a strong attraction for electrons, it just takes them, and you get independent ions with independent charges, okay? But for now, we're going to really focus on these polar and nonpolar covalent bonds. Now, these electronegativity differences are cutoffs, right? Sometimes you'll see the cutoff between nonpolar and polar as 0.4 and between polar and ionic as 2.0. Okay, so keep that in mind. Your teacher will kind of let you know specifically which of those 0.4, 0.5, or 2.0 or 2.1 they want you to use. But it always is that electronegativity difference that we're focusing on. Okay. So let's look at some of these and a little more closely. So in this simulation, we have two atoms. We have atom A and atom B, and I can adjust the electronegativities so I can make it decrease or increase the electronegativity of each atom. If we look and just make them both the same, so both of them have high electronegativities, and we look at the electron density. So again, the evenness of the shading indicates those electrons are evenly distributed around both atoms because they both have the same electronegativity. They both have the same strength of pull for those electrons. If we look at the electrostatic potential, that tells us if there's any net positive or negative parts to that bond. There's not, because notice it's neither red, there's no red or blue regions, everything's just white, which indicates that those electrons are being distributed evenly. Bond character is how the greater the difference in electronegativities, the more we're going to push it towards an ionic bond. Okay. Notice that it doesn't matter. I can have two atoms that have very high electronegativities. I can have two atoms that have very low electronegativities. As long as the difference is small, less than that 0.4, 0.5 cutoff, we have a nonpolar bond where electrons are shared evenly between all the atoms, and there's no positive or negative regions in the bond because of that. If I change this, so if I keep the yellow atom on the right and the green atom on the left, if I keep the one on the left as it is, and I increase the electronegativity of the element on the right, now notice the situation has changed, right? If we look at the electrostatic potential, now we have positive and negative regions of that bond because atom B has a large enough electronegativity higher than atom A that it's strong enough in its attraction for electrons to pull and attract those electrons, more electrons to it. And so we get this partial negative region. Notice the delta negative, which leaves atom A with the less electronegativity, doesn't have as strong of attraction, leaves it with a slight partial positive region to it. Okay. Notice our arrow pointing towards the more electronegative atom. So this would be a polar covalent bond. Right? If we look at the density, we can see, right, we have much stronger, darker shading around atom B compared to atom A. Why is that important? Well, if we look at an electric field, right, if I spin this bond so that the side of the bond with the partial positive charge is lined up with the positive plate, notice what happens. That bond will spin to line up so that the oppositely charged regions line up, so that the region of the bond with the partial negative charge lines up with the positive plate. Right? If I were to make this a non-polar bond again, so if I adjusted things so that we have a very even charge, right, that bond is not going to respond to those charged plates, right, because there's no partial positive or negative regions in that non-polar bond. So there's no behavior change. There's no response when it's put into that electric field. Again, different than, right? If I have a polar bond, it's very different. Polar bond like this one, if I spin this so that the partial positive region around A lines up with the positive plate, it's going to spin so that the oppositely charged region and plate line up. Next week, we're going to really focus on how having polar bonds in molecules can affect their properties and can affect whether or not a molecule is polar or not.